I'm Leopold, and my partner, who you'll be hearing more from later, is Brendan O'Neill. Alright, so we've been doing data transmission, and data transmission is the process of sending digital or analog data over a communication medium to one or more computing network or communication or electronic devices. So it's basically how information goes from one point in a network to another. Alright, and first let's go through a few terms. The first is going to be data packet. So a data packet is a small chunk of an original message, basically represented through its binary data as it's transmitted through a network that stores the information itself, and its direction, and some other metadata. The next thing I'll be talking about is data switching. Data switching is how data is organized as it moves through a network, and basically the path it takes, or the method by which it goes through it. In certain types, it can take different paths. The same data can take multiple paths. In others, it can only take the one path. And this affects the speed, efficiency, and consistency of the data transmission. The three main types are circuit and packet, and the sort of in-between type, which is message switching. The last thing I'll be talking about before I go on to my partner is going to be congestion. And congestion is basically it's what happens when there's more data going through the network than what can be handled. When this happens, performance will often degrade, and since there's more data than can be handled, some data will have to be dropped, and the protocols, which my partner will be discussing more, decide which are dropped and which are kept.
The fourth term is deadlock. A deadlock is a situation in which two or more communicating computers are each waiting for the other to send a message, and thus neither ever does. In a networking environment, deadlocks can occur due to lost or corrupt signals during communication. The fifth term is flow control, which is the management of the flow of data among two different network devices. This is especially important in cases where the sending device can send data much faster than the receiver can digest it. The sixth term is protocols. A network protocol defines rules and conventions for communication between network devices. A protocol is, in one sense, nothing more than an agreement that a particular type of data will be formatted in a certain way. Protocols are necessary because they include mechanisms for devices to identify and make connections with each other, as well as formatting rules that specify how data is to be packaged into messages that are sent and received. The seventh term is data integrity, which is the overall completeness, accuracy, and consistency of data. Integrity is necessary when sending data over a network because it's important to both the sender and the receiver that the data that's being sent is error-free. Error checking and correction protocols will help to ensure that data has integrity. The final term is error checking. Error checking is a process of detecting an error that might occur during the transmission between the sender and the receiver. There are generally three types of error checking. The first one is parity. Parity adds a single bit that indicates whether the number of 1 bits in the preceding data is even or odd. If a single bit is changed during the transmission, then the parity will change, and thus an error can be detected. The second type is checksum. Checksum is a digit representing the sum of the correct digits in a piece of stored or transmitted digital data, against which later comparisons can be made to detect errors in the data if anything has changed, because the sum will change. And the last type is redundancy. Redundancy is the concept of using extra bits to detect error in data. When a receiver receives the data, it passes it through a checking function. If no error is detected, then the important part of the data will be kept and the redundant bits are discarded. Otherwise, it'll ask for a retransmission of that data. Now, the next section we will be looking at is the protocol section. So, there are many important protocols in data transmission, but these are some of the most important ones. So, the first two are TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. Now, these are both responsible for transferring data over the internet, as they are both in the transport layer, but they transport that data in different ways. So TCP is called a connection-oriented protocol, meaning that you have to have a semi-permanent connection made before any data transfer can occur. Now, this provides reliability, however, it's slower. And so if you're on a time crunch, this won't necessarily be the kind of protocol that would be used. So TCP actually determines how to break the packets up. It's suited for higher reliability and less important time constraint. It rearranges packets into whatever the specified order is, and it provides flow control and congestion control, which is important. And finally, it provides error checking, but not only that, it provides recovery. So if there is an error, it doesn't just discard the information, it will retransmit the information and try to figure out where the error has occurred. Now, UDP, on the other hand, is called a connectionless protocol. So this means that one device would send the data to a receiver or multiple receivers, but there would be no actual connection ensured between those devices. And therefore, there's no guarantee that that information will be delivered. UDP is suited for apps that need fast, efficient transmissions like video games, and it doesn't put anything in an inherent order because all the packets that are sent with UDP are independent of each other. UDP is faster because error recovery is not attempted. So if there's an error, it will just discard that data. And finally, the packets are only checked for integrity once they're received, and there is no flow control. So you can think of TCP as a truck. It's more reliable and you can carry more information, and it's slower, whereas UDP is kind of like a motorcycle. Now the next one is IP, or Internet Protocol. Now this is in the network layer, and it sets the rules for sending and receiving data over the internet. IP allows devices on multiple platforms to communicate if they're connected to the internet, and all devices must have an IP address, which allows the network to know where to send the data, and it uniquely defines the device. Now, IP is responsible for encapsulating the data, and it doesn't establish connections or determine the packet order. One technical constraint of IP is packet size, so how large the information is. Now, the next protocols are HTTP, Hypertext Transfer Protocol, and HTTPS, Hypertext Transfer Protocol Secure. Now, these are systems by which devices request internet servers to send the contents of websites, and these are submitted through online forms. Both are in the application layer. HTTP defines how messages are formatted and transmitted on the internet, and it defines what actions web servers should take in response to various commands. So commands such as entering a website, and the HTTP protocol will go and take the information. It will tell the server to send the information for a specific website. Now, it's called a stateless protocol, and this means that each command is executed independently and without any knowledge of the commands that came before it. So HTTP will not remember what website you sent in the past. Cookies and other things were developed to kind of work around this issue, but HTTP itself does not do that. Now, HTTP has status codes, and these help servers and clients to identify a problem that has occurred. So common ones are the 502 error or the 404 error, meaning that a link was broken or deleted and the information you're looking for doesn't exist anymore. Now, HTTP is not secure. However, HTTPS is very similar to HTTP, and this is secure. It provides security and privacy, and it provides more data integrity. So HTTPS uses the transport layer security protocol, which is at the transport layer. Now, the next protocol is SMTP or Simple Mail Transport Protocol, and POP3, which is Post Office Protocol version 3. These are application layer protocols, and they're used to transfer email. SMTP is only used to send emails, and it does not receive them. What it does is it listens for a TCP connection to an SMTP server, and once a connection is actually made, because TCP has to have a stable connection, then it will send the email. POP3, on the other hand, does not send emails, it only receives them. And once emails are received, they're held by the internet server until the client downloads them. And then once the client downloads them, then the emails are deleted from the server. Second to last, we have MAC, the Medium Access Control. And this protocol is in the data link layer, and it controls the hardware that's responsible for the interaction with the wired, optical, or wireless transmission media. So this controls the hardware in the computer that interacts with the external hardware that will bring the information into the computer. Now this provides flow control and for the transmission media and multiplexing. Now it encapsulates higher level data information into information that's appropriate for the transmission media to handle, and it identifies transmission errors, and if there is an error and the data is not delivered, then MAC will retransmit the data. Now finally, we have BEB, or binary exponential backoff. Now this is an algorithm, and it's used when multiple devices are trying to access one internet resource at the same time. Only one entity can access that resource, so the others will have to wait and retry when the resource becomes available. Now, this is why binary exponential backoff was created, because it'll determine how long entities should have to wait before they retry accessing that information. With every unsuccessful attempt of a device to access the information, the protocol will increase the interval, in fact, double the interval of time before that connection is tried again. And this prevents congestion of information, and it reduces the probability that multiple devices will request to access the same resource at the same time, and this therefore improves the system efficiency. Now we will talk about the OSI model, which is the Open Systems Interconnection Model. Now, this is a conceptual model which, quote, standardizes the communication functions of a computer system without regard to its underlying internal structure. Now, this is important because it can be applied to a variety of diverse computer systems, and it's true across all of them regardless of their actual hardware. Now, the OSI model is broken up into 7 layers. It's broken up into the physical layer, the data link layer, the network layer, the transport layer, the session layer, the presentation layer, and the application layer. And each of these, the functions of each layer builds onto the layer below it. So the first layer, the physical layer, transmits raw, unstructured data over the physical medium, whether it be fiber optics, wire, satellite communication. And what it actually does is it converts digital bits into electrical, radio, or optical signals that can be used to actually transfer the information. And the physical layer also defines certain characteristics like the maximum transmission distances or the actual physical connectors. Now, the second layer up is the data link layer, and this provides node-to-node data transfer. So it links two directly physically connected devices, which are the nodes, and it can detect and correct errors that occurred in the physical layer, and it defines the protocols to establish and terminate connections between devices and protocols for flow control, so managing the flow of information. The next layer, the third layer, is the network layer. This layer determines the physical path that the data will actually take from the sender to the receiver in the network of nodes. It's a medium in which many devices nodes can be connected, and each node has its own address. Now, if a message is too large for one data link between two nodes to handle, the network protocol can split the data into multiple pieces and send it through different pathways, different nodes, and still have that information all get to the destination that it's looking for. Now, networks may report if there's a delivery error, but they may not, and there's no guarantee that information will actually be delivered in this layer. The fourth layer is the transport layer, which provides the actual function of transferring the data. Now, this controls the reliability of the given links and error control. So the transport layer is where it actually determines if there is an error in delivering the information. So it actually provides an acknowledgement that the data was transmitted. And if there's no error that occurs, then it'll send the next data in line. So it's easy to visualize this as kind of like a post office. It deals with the transferring and classification of messages in whatever data is sent, and it only inspects the envelope quote, or the outside layer, the outside package of the information to determine where it's supposed to be delivered. Now, the next layer is the session layer, which establishes and it maintains and terminates connections between devices. You can think of it kind of like a light switch. It turns the connection on or off. Now, the next layer is the presentation layer, the sixth layer. Now, this presents the data to the application layer, which is the seventh layer, in an accurate, well-defined way, and it translates the information from the way the network handles it to the format that the applications need to have the data in. So you can think of it as a translator. And lastly is the application layer. Now, this is the layer where the interaction between humans and computers take place, and the interaction between software on your computer and the actual network takes place. Now, this is where the applications have access to the network resources, and the functions of the application layer are to identify communication partners, determine the availability of network resources, and synchronize communication, among others. And that is the OSI model.
Hello. For my main contribution, I will be discussing the root factors that affect the efficiency and speed of data transmission, and methods used to improve the efficiency and speed of the same. The main factor is that all others are derived from is the traffic load versus the traffic capacity. Traffic in this case is the amount of data that is being transmitted through the network already. Traffic capacity, likewise, is the network's capacity to handle data, represented by buffer space and throughput, which is how fast data can actually be transmitted. Methods of increasing the speed of data transmission either decrease the amount of traffic incurred when transporting the same information, or increase the capacity for a network to handle information. The main method of reducing traffic is data compression, a practice where complex data is put into a format that consumes less space. Using H.264, a commonly used data compression technique, high-quality video can be retained at a 50th of the traffic on the network. This compression is one of the biggest factors that allow network applications to function in real time. In general, the biggest impact on how fast a network can transport a set amount of data, assuming traffic is consistent, would be the transmission media used. The three most common data transmission media would be fiber optic, conductive metal wire, and wireless. Out of these, in terms of speed, consistency, and safety, fiber optics are by far the most effective, though in terms of cost, they are the most costly. Conductive metal wire is a good alternative with ratings in speed, safety, and consistency below that, but being significantly cheaper than the fiber optic method. In these categories, wireless is by far the least effective, with the lowest speed, safety, consistency, and only being overshadowed in the cheapness by conductive metal wire. These rankings may be confusing to some, as wireless is by far the most common medium, but this prevalence is in general due to the convenience of going wire-free. When data is being transmitted through a network, modern systems break that data up into small parts, each labeled with a destination called packets. These packets are sent independently from each other to their destinations, where they are reconstituted to form the original piece of data. This method is called packet switching because of how it organizes the data into packets. Another less efficient method is known as circuit switching, which allocates a dedicated pathway between the data and its destination before sending the data as a continuous stream. This method is less efficient because it is unable to use all the capacity for transmission available to it, whereas with packet switching, data can be transmitted in parallel along different routes through multiplexing. Alright, thanks for listening to our presentation. If there was any area that you feel as if we didn't explain thoroughly enough, please let us know.